Physical reality is a collection of unorganized quantities. We use an abstract layer of symbols, numbers, designed to translate chaotic clusters into logical systems. Our earliest counting systems were built to record presence. If you saw 7 objects, you recorded a value of 7. However, these systems lacked a way to quantify the absence of a quantity. The introduction of 0 by Indian mathematicians provided the logical anchor required for positional numbering. It allowed us to represent nothing as a specific manipulative value. We can visualize this foundation on a coordinate plane. It begins at an origin point of 0 and generates a vector that expands continuously to the right. Along this line, we place our counting numbers, 1, 2, 3, and so on. This sequence is defined as the set of natural numbers, or n0. It is infinite in the positive direction, but physically limited by its origin. There is no mathematical value defined left of 0. Discrete mathematics and early computer science rely on this structure to index and sequence data. It is the simplest way to track the order of operations. However, this counting structure only functions if our operations move in a single direction. To build more complex logic, we have to test how this space handles operations that move backward, toward that 0 boundary. In mathematics, a set is defined by its closure. This means that when you perform an operation on 2 elements of a set, the result must also exist within that same set. The natural numbers are closed under addition. Adding 2 positive values will always result in another value further down the line. Subtraction, however, forces movement backward. It pushes the value back toward the 0 origin. If we take 5 and subtract 6, the calculation reaches 0 and then falls off the edge of the defined number line into the void. Because the natural numbers do not contain negative values, the operation fails. The set is not closed under subtraction. To make subtraction a valid operation, we must expand the physical boundaries of our mathematical space. The number line extends symmetrically to the left of the origin, creating a path for negative values. This bidirectional, infinite sequence is known as the set of integers, represented by z. The operations we need to perform define the architecture of our data. When the natural numbers were too small to contain the results of subtraction, the system itself had to grow. Within this expanded integer space, arithmetic operations function as recursive spatial algorithms. Multiplication is defined as looped addition. To multiply 7 by 4, we take an initial cluster of 7 and generate 4 identical copies, merging them into a single array of 28. Because integers have signs, the resulting product follows a specific rule. An even number of negative signs makes a positive, while an odd number makes a negative. Now, exponentiation is looped multiplication. Squaring a number arranges it into a 2-dimensional grid. Increasing the power to 3 extrudes that flat grid into a 3-dimensional cube. Division follows the same recursive logic in reverse, functioning as a loop of repeated subtraction. Dividing 19 by 5, the algorithm extracts groups of 5. Each group removed represents one successful loop. The process stops when a value is too small, leaving 4 units behind. This remainder is expressed through the modulo operator. 19 mod 5 equals 4. Modulo is more than a byproduct of division. It is the primary tool used in data science to determine divisibility and cycle through finite data sets. We define a factor based on this modulo result. A is a factor of b if b mod a equals 0. Meaning the division loop finishes with nothing left over. Factors usually appear in pairs, such as 2 and 6 for the number 12. Perfect squares are the only exception, as one of those factors is simply the number multiplied by itself. This logic leads us to prime numbers, integers that have exactly 2 factors, 1 and themselves. There is no simple equation to predict where primes occur. As we move toward infinity, identifying them becomes a massive computational challenge. We isolate them using the Sieve of Eratosthenes, systematically eliminating composite numbers from a grid. We remove 1, as it has only one factor. The algorithm flags 2 as prime, then removes its multiples. It moves to 3, eliminating its multiples, and so on. As the sieve iterates, it clears away every number that can be divided. The survivors are the primes, numbers that cannot be expressed as a product of any other integers besides 1 and themselves. Primes are the elementary components used to construct every other integer in the system. Through unique prime factorization, we break a number down into its constituent parts. 12 decomposes into 2 and 6, which further breaks down into 2 and 3. Expressed with exponents, we write the prime map of 12 as 2 squared times 3. This applies to any integer. If we take 126, the branches cascade downward until we reach the base prime factors. 126 is built from a specific combination of primes, 1, 2, 2 3s, and 1 7. This is the fundamental theorem of arithmetic. It states that every integer has a single, unique prime signature. No two different numbers share the same prime decomposition. These primes are the indivisible units of the integer system. By understanding how they combine, data scientists can build algorithms that rely on the consistent, unique identities of every number in the set.